So, good afternoon all.
Good afternoon, ma'am.
Um, in today's session, we are going to discuss about practicals that we are going to conduct in digital design and HDL. Okay. So, in earlier sessions, we have discussed about how to use Xilinx ISD. Then after that, we have seen how to simulate program using HDL, VHDL. Okay. So, uh, the same software that we can use for the Verilog languages because this Xilinx are that supports both Verilog as well as VHDL language. So now in today's session we are going to discuss about how to simulate programs using Xilinx ISV. Okay. So as you know that for that we need to open a window for this. Wait a minute. I will share my screen. So uh, we need to open Xilinx ISV. So here now earlier version that we have seen in the last few sessions that was uh, Xilinx ISV 14.7 only, but it was related with the Windows 10. Okay, now as on my laptop I have Windows 7. So this version is little bit different than that of the earlier version that you have seen, but still we have the same programming strategy, so that will not make difference here. Only little bit Windows that that you find on this version that will be slightly different than that of the earlier. Okay, so here as we have clicked on this Xilinx ISE shortcut. Okay, so it will open this window. Okay, click on file and click on new project. Okay. So give the name to this new project. So now today we are going to perform uh, Verilog code for half adder as well as full adder. Okay, so these two programs that we are going to simulate using Verilog HDL. Okay, so as you know that this Verilog HDL, that is another hardware description language that is used in digital systems. So we are going to use now that in earlier practical we have seen about the VHDL. Okay, so today we will go for Verilog HDL. Now give the name to this project. So I'll give the name to this project as initially we will simulate half adder and after that we will go for full adder. So I'll give the name to this as a project as a half underscore adder. Okay, so this is the name that I will give. Okay, remember that here there will be one uh, option that you will get that selects the type of top level source of the project. Okay, you can see there are different options, that is a HDL, schematic, IDIS, NGC or NGO. Okay, we are not going for these other options, but we are going for the HDL because we are using their HDL um, That is a language, Verilog or VHDL. These two languages that we are going to use. So our source type that will be HDL. Okay. So then click on next. Now here this new window will open which is showing new project wizard. So there, as we have earlier said, property name that will be value, then evaluation development board that is a non-specified, then product category that is false. Okay, so this will be the by default. Here in a family, you need to select any one of the device. Okay, so the first that family of the programmable device that you need to select. Now here you can select whatever we are going to discuss in our theory classes. Okay, in the theory classes now we are discussing about uh, commercial devices that are available. Okay, so this Spartan 3 that is one of the commercial device that is available in the market. Okay, or that is it is a family, and in that there are different. This is the CPLD that is a yes.
Excuse me, ma'am.
Hello.
मॅम तुमचा आवाज खूप ब्रेक होतोय.
Wait a minute. Actually, today I have a lot of network issues, so that is why. Check now. Am I audible now? Hello.
Yes, ma'am.
Am I clear? My voice is clear.
Yes, ma'am. It is good.
Actually, because of the weather, I can have that much good network, but okay, we will manage. Okay, so here we need to select a family that is a Spartan 3, that is a CPLD, complex programmable logic device. So that we are selecting, and then from that we are selecting a device. Okay, so we will select XC3S250E. Okay, or we can go for this XC3S500E. Okay, so these are the different devices that are available in the market. So out of that, we are selecting any one of the device. Okay, then package that is a VQ100 or different packages that are also available. We will select VQ100. Okay. So okay, now this selection that will depend on which board that you are using. Okay, so whatever, as I earlier said, that whatever board that is available in your laboratory, so depending on that we need to select or we need to choose these options. So now right now we are selecting this, and we are just simulating right now all these programs, so that will not make much difference. Okay, then already we have selected this speed that you can select from -5 or -4. We have selected it as a -4. Then already we have selected top level source type, that is a HDL. Okay, so that will be now disabled here because already we have selected in the first window. So right now it will be disabled. Then synthesis tool, that is a XST. So it may be VHDL or Verilog. Then for the simulator, iSIM simulator that we are using, so it will be again VHDL or Verilog for both these. So it will be there. Okay, so here we are using iSIM. So we are not going for model SIM. So we are going for iSIM simulator. Okay. Then now as we are going for the Verilog language, so here select preferred language as a Verilog. Okay. Now though if this preferred language option as a VHDL, then also it will not make difference. That is the your choice that you are having. Okay, so you can preferred language maybe VHDL or Verilog, but as we are going for Verilog HDL, so I am selecting this as a Verilog. Then the next, that is a property specification in project file, that is store all values. Then manual compile order that we are not selecting, that is a checkbox that we are not selecting, and VHDL source analysis standard, that is a VHDL 93. Okay. So here then we are disabling enable message filtering. Okay, so all these settings once we have done, we will go for the next. Okay, so here you will find summary of whatever project that you are doing. Okay, so in this window now you can see all the summary. So here you can see that now you have selected preferred language as a Verilog. Okay, so all that summary that you will find in this window, and then click on finish. Okay. So you can find here now whatever project that you are designing that is present in this window. Okay, so in this portion you can see the name of your project. Okay, right click on that and click on new source. And now here we are going for the Verilog HDL language. So here select on Verilog module. Okay. Now whenever we are going to write a program in a Verilog, so we call that as of module. So you can see here this Verilog module. Click on that and then give the name to that file. Okay. So whatever source that you are designing, give the name to that source. So I'll give the name as a HF or H underscore adder. I'll give this name. Okay. Then check for the location where you want to store this program. Okay, so I am going to store it in a on a desktop VAP folder. So in a project that is a half header. So click on next. Now here you will find that whatever is the input and output port declaration, that part you can see here. So here this is the new source wizard window that will open, in which you need to define module. Okay. As in a Verilog we have the module. So here you need to specify ports for that module. Here name for that module, it will be by default taken as whatever is the name that you have given for that source. Okay, so we will keep that. And then now mostly keep the practice. Okay, so now as we are going to have separate modules, so it will not affect on the simulation, but always keep the practice that you should declare output port first and then go for the input ports. Okay, so this is the some rule that in a Verilog we define output port first and then output port. So in that way we will have declaration of output port first. So which are the output ports for half adder?
Sum and carry.
So sum, that is the one output port. So I'll give okay sum, and another that is a carry. So Cout. I'll give the name to that port as a Cout, and remember to change the direction to output. Okay, so these are the two output ports, and then the input ports are, let us say, A and B. These are the two input ports. Okay, so as we know that for a half adder there are two inputs. Okay, we are discussing about this single bit half adder. So here it will be two input ports and two output ports. That is the A and B. These are the inputs, and sum and carry out, that is the output. Okay, so click on next. So here you will get the summary of whatever source that you are designing. Okay. So this here you can see that it is added to project or not. So that is there. Then it is a Verilog module, the name of that source, and then all the ports that will be defined here. Okay. And then finish. Okay. So wait a minute. So here you can see that the first line of this module, that is a single quote time scale, and then after that 1 nanosecond oblique 1 picosecond. Now what is defined? It is the time for this module, that is a 1 nanosecond, and this indicates precision of that time. Okay, so whatever is the timing, so delay timing, so that is specified here. Okay, now this precision, okay, or these values that are given in the in the form of 1, then 10 and 100. Okay, now unit for this time, that may be second, then millisecond, nanosecond, picosecond, femtosecond, okay, whatever may be there, but this number is always 1, 10 and 100. Okay, so that is why in our test, okay, we had one question, that which time scale is wrong. Okay, and most of you have given the answer as a 1 nanosecond oblique 1 picosecond, but it is the correct one. But there is there was one option, that is 100 nanosecond oblique 110 nanosecond, picosecond, something like that was there. Okay, and that was wrong, because this number should be always in the range of 1, 10 and 100. Okay, so फक्त आणि फक्त 1, 10 किंवा 100 असाच असला पाहिजे, दुसरा नंबर इथे असणार नाहीये. So and that is why, so that option was wrong. Okay, so this time scale, that is indicating delay time period and then precision. Okay, so after that all the comments that you can see here, that is a company name, then engineer, whatever, then creation date, design name, module name, project. Okay, so all these will be there, and then it is a module. Okay, so module name, that is a H underscore adder and then bracket, and in that you can see all the ports. Okay, so here first, that is the output port sum, then output C out, input A and input B, bracket complete, and then semicolon. Okay, and then now here we are going to declare whatever Boolean expressions that we are going to execute. Okay, so we will assign sum equal to A XOR. So what is the which symbol is used for the XOR or operation? Which is the operator that is used? XOR साठी कुठला ऑपरेटर वापरतो?
ते रेस्टूचा सिम्बॉल रेस्टू साठी आपण यूज करतो.
Exponential symbol. Okay, so this is a exponential b, that means actually it is a XOR b and then semicolon. Okay, whenever you are completing that assignment statement, then you can give a semicolon here. Then again another assign C out is equal to A. What is the expression for C out? A and B. Okay, so the symbol that is used, that is ampersand, A and B and then semicolon. Okay, and then it is the end of model. So here there is no semicolon after end module. Okay, so this is it. Now this is the keyword that is used in a Verilog HDF. Here you can see that only module keyword is used to begin the module. Okay, but there is no any begin module type of keyword. Okay, so again there was one question in your test, that is the begin module or end module. These are the keywords in Verilog, and that is a false. Okay, only module is a keyword. Begin module is not a keyword in Verilog. Okay, so this is a complete program for half adder. Okay, save this. Okay, so design is also completed successfully. Now synthesize this. So first of all, we will check for the syntax. All the procedure that is same as that of the VHDL, how we have done. Okay, only the language that we have changed. Okay, so you can see here that process check syntax that is completed successfully. So that means whatever is your syntax, that is correct. Okay, and then we will go for view RTL schematic. Okay. Click on this start, and here you can see that RTL schematic for this half adder. Okay, so here you can see this all the connections for your half adder. Okay, so these are the inputs and these two are the outputs. Okay, so this is the RTL schematic. You can also check technology schematic by clicking on view technology schematic. And here you can see. Now if you click on this box, okay, here if you click on this box, this will open where this is nothing but for the cout, that is output, and inputs are okay. Now here you can see the input names that are default because these are the inside whatever is the inside these nodes or names that are given, so that we will proceed at this gate. Okay. Now you can check for the truth table for this. You can also check for equation. Okay. You can go for K-map. This is the schematic that we have. Okay. So this is again for the sum output. So sum. Here you can see truth table. So by checking this truth table, you can verify whether it is a correct circuitry or not. Okay. So that is a view technology schematic of this half adder. Okay, so now we have simulated this program. Now we want to test our program. And so for that we need to write a test bench. Okay, so click on your project name. Okay, right click on this and select new source. And now select Verilog test fixture. Okay, so this option you need to select now because we are going to write a test bench for this program. Okay, so this you need to select here Verilog test fixture and give the name to this. Okay, so I'll give the name as a half underscore adder underscore teach. Okay, and then again check for the location. By default, whatever you have selected earlier, it will take it as it is. And if you want to change, you can click on this browse option and then you can go for the another location. Okay, I will keep it as it is. Add to project, select this, okay, check box, and then go to next. Okay. Now, this new window that will open, which will define or which will say about the whether you are going to associate this source with which one source. Okay, if with a certain source. So here we are going to associate our test bench with this h underscore adder source. So that is a Verilog program that we have written, and then click on next. So here you will get the summary for this and then click on finish. So now here you can see that this test bench that will open, and now here we need to select. We need to give or instantiate certain stimulus for this unit under this. Okay, so here you can see that this is the module h underscore adder underscore tb, and then you can see that here inputs A and B, these are now here in this defined as a register. Okay, but you can see that outputs are shown by YF. That means these are shown with a defined with a net. Okay, So always remember that outputs are defined in always as a wire or net. It may output may be as a register or a net, but whenever we are going for test bench, so it will be always shown as a wire. Okay. Then instantiate the unit under test. So here we are instantiating that unit. So this is the all the ports that are defined here, and then we are going with the initialization of the input. Okay, so initial begin. So here initially A and B both inputs that will be assigned with the values 0, and then that means we are resetting this circuitry, and then we are waiting for 100 simulation time. Okay, so here this is the 100 nanoseconds. So 1 nanosecond, that is the time period that we have selected for the simulation, and then here that means this whenever we are saying hash 100, so it will consider as a 100 nanoseconds. So that is the time period. So this reset conditions will be there for 100 nanoseconds, and then we are going to add certain stimulus here. So I'll copy this part, okay, and then so that will make easier for me to give the different inputs. So I'll paste it here. I'll remove this part, this comment, because I don't want to see this. This is not the initial. I'll change A to 1 and B to 0. Okay. Then I will again I will wait for 100 nanoseconds. So I will now this I'll copy this, and then I will paste it. This is my another condition where I am going to make A equal to 0 and B equal to 1. Okay. Again I am going to wait for 100 nanoseconds, and then this is both now A and B that I am going to make it as a 0. Okay. So wait for 100 nanoseconds, then end of this begin and end of the model. So whatever initialization that we have done, we are going to end it here, and then we are going to end the model. Okay. Save this. Okay. Then select option, that is the simulation. So iSim simulator that we have selected, and click on your test bench source. So click on this. You will find in this window, process window, you will find here iSim simulator. So expand it and click on behavioral check syntax. Okay. Now as your code is correct, so it will click show correct option, okay, and then click on simulate behavior. Simulate behavioral model. So we are simulating this. So your simulation, this is showing that your simulation that is running. So it takes a little time, extra time than that of the earlier version that we have used. But as because of lockdown, I can't go to college, so I'm doing it on my laptop. So let us have certain patience, as it is taking some little bit extra time for simulation. So now here you can see that this simulation window that will open where you can see the waveform, and whenever you are zooming it, okay, so you can see this. Okay, so if you click on this, you can see that whenever in A is 0, B is 0, sum is 0, carry out, that is also 0. If you click on this time period, so here A is 1, B is 0, sum is 1, C out is 0. Okay. Now next is B1, A0, sum is 1, C out is 0. Okay, and if you click on this A1, B1, sum is 0, C out is 1. Okay, so this means that whatever is the truth table for half adder, that is verified here. Whatever code that we have written, that is the correct code, and then so here we have the correct code for that we have written, and then we can go for manufacturing of this. Okay, so now you can use after this simulation, now you can use any commercial device, that is a programmable logic device, and on which you can have this program. Okay, so this is about the half adder using Verilog HDL. So if anybody has any doubt about this, yes, any doubt? All of you understood how to do this? How to compile your program, how to simulate? Okay. Now, now if you look here, okay, or here also, you can see that on the waveform of A, that is the input, here you can see certain words. If you zoom it, you can see that it is a V. Okay. So this is showing that it is a variable. Okay. So here you can see this option, that is a variable. Okay, so I have removed this, and then this is a internal signals, sum and cout. These are the internal signals. So here you can see the plus sign on this. Okay. So now so these are the two internal signals, so which are present. Okay, so we are going to check here, and then these A and B, these are the variables. So these on this we are giving certain phase signals, and from that we are checking this sum and cout output. Okay, so this is about the simulation of half adder using Verilog HDL. So if anybody has any doubt, they may ask. Otherwise, we will proceed for the next circuitry. No any doubt?
No, ma'am.
Okay. So now let us discuss about full adder. Okay. So I'll go for new project now. Okay. Before that, I will close these. And now I will go to new project. I give the name to this project as a full adder. Okay. So all the options for the project setting, that is the Spartan 3, this family that we are selecting, then device XC3S500E, and package, that is a VQ100 that we are selecting, and we are selecting language, preferred language as a Verilog. Okay. Click on next. and click on finish after checking for this summary. Okay, so click on finish. Now you can see here your new project. So right click on that, click on new source. Okay, then which option we have to select? Verilog model, and then give the name. Add to project and then next. Okay. Now you tell me what are the different ports in full ladder.
Ma'am, output again the same sum and carry and input A, B, C in.
Okay, so I'll give the name, that is the sum. Okay, so this is the output port. Then C out, that is the again output port. Okay, always initialize output port first and then go for the input port. Okay, so I'll input A, then B and C in. These are the three input ports. Okay, so click on next. So here you can see the summary of your new source. Okay, so all the ports that you can see, and then click on finish. So here you can see time scale, that is a 1 nanosecond. That means one simulation time, that is it is considering as a 1 nanosecond, and precision, that is of a 1 picosecond. Okay, you can change it to 100 picosecond also, or whatever required, but we will keep it this as it is. Okay, and now here you need to assign the Boolean expression. Okay, so whatever expressions that you want to define. So assign, what is expression for sum? Sum is equal to
A XOR B XOR C in.
A XOR C out is equal to what is expression for
AB
C out?
AB plus AC plus BC.
That means A and B or, so or operator, then so whether it is all expressions are correct? Yes?
Yes, ma'am.
Okay, so let us save this. So our hierarchy that is successfully completed. Okay, and then we will check for syntax. Okay, now what it is showing? That your syntax is not correct. Okay, process check syntax failed. Can anybody tell me why it is failed? Look at the program and tell me why this syntax checking is failed. Just check for this program. काय चुकलंय प्रोग्राम मध्ये की त्यामुळे आपल्याला सिंटॅक्स आपला चुकीचा आला, फेल झाला? With your keen eyes, look for this program. Yogesh, can you tell me what is wrong in this program? Rahul, are you there? Rahul?
Yes, ma'am.
Yes, what is wrong in this program? Why our check syntax failed? If you look at this line, okay, you can see that what we have written, sum is equal to A XOR B XOR C. But what is B? B we have written as a capital B. Okay, but whenever we are declaring ports for this module, we have written B, that is in a small letter. Okay, now as we know that Verilog is a case sensitive, and that is why it shows error while simulating. Okay, so if you look for this here, okay, you can see that this error was f underscore adder dot b, line 28, b has, the capital B has not been declared, because actually it is not present in this code declaration part, and that is why it has shown error. So we need to make it as a small case B. Okay, and now we will save this, and again we will check for the syntax. Okay, and now you can see that your process check syntax completed successfully. That means whatever syntax, that is correct. Okay, now let us see RTL schematic. Here you can see RTL schematic for this full ad. Okay. Similarly, we can go for technology schematic. Okay. So here you can see this circuitry for C out. Okay, so these three inputs, that is the A, B, C in. Okay, so we now here they have considered internal signals. Okay, similarly you can go for this also. So this is the schematic for sum. Okay, so these are these many logic gates that are used to get a sum output. Okay, so these are the three inputs, and this is the output. Okay, so you can check for the truth table also. From that you can verify whether it is correct or not. Okay, so this is the schematic for full adder. Okay, now once this is checked, we can go for the test bench. Okay, so to check or to test whether the circuit is correct or not. Okay, so we will click on our project name and then right click there and open new source. Okay, then go for Verilog text fixture. Give the name to this. So I'll give the name as X underscore adder underscore TB. Okay, so this is the name for my this new source, and after checking the location, selecting or adding this to project, go for next. Okay, associated source with this test bench, that is F underscore adder, and then next. This is the summary of your new source and then click on finish. So here this test bench file that will open. Okay, here you can see that all the inputs that are like a register, okay, and these are all the outputs that are of a net type, that is a wire. Okay, so this f underscore adder, that is the unit under test, okay, that will instantiate or the program that we have written there. Okay, that means it will instantiate the component f underscore adder in this program. So all the ports that will be mapped with the ports in this unit under test. Okay, and after that, initialization of the input. So initially, all the inputs that will be assigned to the value 0. That means it will be the reset condition. And then after that, we need to stimulate all these inputs. Okay, so we are going to add stimulus here. So I'll give the input, that is a 1 0 0. I'll remove this comment. And then I'm going to add different input vector. I hope we have already almost given all the combinations for the input. Okay, so then end of this initialization, that is adding the stimulus to all the inputs, and then end of the module. We will save this. Okay, then go for the simulation. Select test bench module. Expand iSIM simulator and check for behavioral syntax. Okay. So there is no any error. So let us simulate now behavioral model. And now here you can see the output waveform. So initially we have kept 000 state for 100 nanoseconds. So for this much time period. So you can see that for 000 condition, sum is 0, carry is also 0. For the next condition, that is A is equal to 0, B is equal to 0, A is equal to 1, B is equal to 0, and C is equal to 0. Sum is 1, carry 0. Okay. So next is 0 1 0, sum 1, carry 0. Then for 1 1 0, sum 0, carry 1. Again 0 0 1, sum 1, carry 0. 1 0 1, sum 0, carry 1. 0 1 1 condition, sum 0, carry 1. And the last condition, 1 1 1, that is all the inputs are 1, sum is 1, carry is 1. Okay. So that means all the conditions are verified here. We got the same result as per the truth table when we simulate this program. That means our program is correct. So that is about the simulation of full adder using Verilog ST. Okay. So anyone has doubt about this simulation?
No, ma'am.
Okay. So everything is clear. Now you can go for another type of modeling also. So that also you can do. So as we have used always statement also. So that block, always block that we have used, using that also you can do this simulation. Okay. So that we will see afterwards how we can simulate that. So that is about the simulation of full adder using Verilog HDL. So in this session, we have completed our second experiment, that is uh, simulation of half adder and full adder using Verilog HDL. If you have any doubt, you can ask me. Will have doubt? काहीच बोलला नाही तर त्याचा अर्थ असा होता की तुम्हाला सगळं समजतंय. सगळ्यांना सगळं समजतंय का? Okay, that's good. That you all are understanding everything. Okay, जसं मी नाही बोलत आहे त्याचा meaning मी तरी असंच घेणार आहे की तुम्हाला सगळ्यांना सगळं समजतंय. Okay, so for today we will stop here. In the next session we will again discuss some more programs in a practical session, and in a theory sessions we are going to continue with the architecture of commercial devices. Okay, so for today we will stop here.